Professor Nandip Dekaburua sir is a professor of Department of Mathematical Sciences at Tezpur University. He is known for his work related to mathematics of Ramanujan. In particular, he and his collaborators have found several Ramanujan type congruences using different methods. He graduated with a master's in mathematics from the Indian Institute of Technology, Kanpur, India, 1995, and a PhD in mathematics from Tezpur University, India, in 2001. Following a short stint at Assam University, Silchar, he has been a member of the faculty at Tezpur since 1997, becoming a full professor in 2009. For a period of 1 year in 2006 to 2007, he was a visitor at the University of Illinois Urbana-Champaign, working with Bruce C. Bandit. He has been a recipient of the Young Scientist Award from Indian Science Congress Association in 2004 and a Boy Scouts Fellowship from the Department of Science and Technology, Government of India in 2005-06. Professor Borua has written over 50 research papers so far related to spatial functions, modular equation, basic hypergeometric series, and partition of number theory. He is also associated with giving several popular lectures for school and college students in different places of Assam as in other parts of the country, and is a member of the advisory board of the online magazine Gonitchora. He is a member of several distinguished professional societies and serves on several committees related to education. He has been serving as a referee of research articles of over 30 journals of repute, like Journals of Number Theory, Elsevier Journal, Journal of Mathematical Analysis and Applications, again Elsevier Journal, Journal of Computational and Applied Mathematics, again Elsevier Journal, the Ramanujan Journal, Springer. Sir, we are eager to hear from you. Over to you, sir.
Acha, Bapan. Hello, Bapan.
Yes, sir. Yes, sir.
Before Nandip Dekaburua takes over, I would just like to add for the benefit of the audience, just one word. Nayandip, if I remember correctly, Nayandip Dekaburua had done independent PhD work. He did not do his PhD research under somebody's supervision. It was almost an independent work, and he registered at Tezpur University. I hope I am correct now.
Sir, Professor Bhattacharya was my formal guide.
Was a formal guide. You did it independently. Yes. I know. You did it independently because the rule. Permit anybody without having a supervisor, informal supervisor, take that. I remember that. But anyway, this is a very important and interesting thing. Independent research. Thank you.
Thank you, sir. So, thank you so much, Professor Singh, Buragoi sir, Professor Devi, and other colleagues of Royal Global University. In fact, I have visited thrice, in fact. Before the building came up, a team of our Tezpur University, we visited that site and took stock of the progress, etc. Then I next visited with Professor Bruce C. Barnt. He came to Tezpur University to deliver some talks. And on the way to the airport, we visited your university. And he actually delivered a talk on Ramanujan. And then again, I delivered a talk in that university, Royal Global University, a few years back. And that is also on Ramanujan and pi. So thank you so much. And in fact, one of my students is there in the Department of Mathematics. Okay. And so I start my talk on Ramanujan and a glimpse of his mathematics. It is not possible to tell all about his mathematics in just a 1 hour talk. So I will choose some special topics to discuss his contribution and how from a small thing, how he made it very big. In each of these topics, his contribution was immense. So for the network problem, I will stop my video and I will share the slides now. So if there is any problem, please, I request the moderator to please convey this to me. Okay, is my slides visible?
Papan, are you here? Yes, it is
Yes.
visible.
Okay.
Sir.
So this, so this is the title of my talk, Ramanujan, a glimpse of his mathematics. And this is my email address. And so I have written this, that this has been delivered here. So as you already know that he was born on December 22nd, 1887 in Erode, Tamil Nadu. And in fact, in his maternal grandparents' house. And it was the customary at that time that the first child should be born in maternal grandfather's house. So he was born in maternal grandfather's house in Erode. And after a few days, they were moved to the original home at Kumbakonam. And this is the picture of Ramanujan's mother, Kumulata Ammal. And there is no picture of his father is available. So they moved to Kumbakonam, and that was approximately 260 kilometers southeast of Madras. And his family was very poor, economically very poor. And this is Ramanujan's home at Kumbakonam. And as you can see that the condition was not very good. And though this is a picture taken much later than Ramanujan's time. Now this home has been converted into a museum by Shastra University, and they have renovated a few places I have heard, and actually a lot of mathematicians related to Ramanujan are not satisfied with the renovation. They felt that this should have been kept as it is. Okay. This is another picture of a residence home where Ramanujan was staying while he was in Madras. And as a child, he was brilliant. And in 1898, he entered Town High School of Kumbakonam. And at that school, at the age of 12, Ramanujan borrowed S.L. Loni's Plane Trigonometry, Part 2. There are two parts of that book, S.L. Trigonometry. S.L. Loni's Plane Trigonometry. And Ramanujan worked all the problems in that book. Though the name is Plane Trigonometry, but it also had some other topics like trigonometry, calculus, infinite series, complex variables, etc. So Ramanujan worked all the problems in that book and he mastered in these subjects. And at the age of 15, Ramanujan borrowed again from Kumbakonam College Library, George Shubriskar's A Synopsis of Elementary Results in Pure and Applied Mathematics. And he mastered in this book as well. But what is the peculiarity of this book is that this is the picture of the book that I borrowed, that I bought through Amazon. And this book actually contains only formulas. No proofs are given. And in scanty places, some proofs are given, but very sketchy. Those proofs are very sketchy. And in fact, Carr was a tutor at Cambridge and compiled his book of 4,417 results as an aid in his tutoring. So he was a tutor, so he compiled his formulas in this book. And the first formula of this book was the well-known formula a square minus b square equal to a plus b into a minus b. So that is known to everybody. So that was the first formula, but there were many other formulas and geometrical construction and other formulas related to geometry, integral calculus, and series, etc. Okay, so Ramanujan, because there were no proofs, so Ramanujan tried to prove those theorems by himself, and he proved all the theorems there, and also found many new results of its own. And he began to enter his new results in his notebooks. And as in Carr's book, he also did not enter or did not record the proofs of his results. And he passed his matriculation examination and with first class. And for that, he got some Subramaniam scholarship. Junior Subramaniam Scholarship, and with the scholarship, he entered Government College Kumbakonam. But by that time, he was totally absorbed with mathematics. So at the end of the first year, he failed to pass in the examination and lost his scholarship. And because their family was very poor, so Ramanujan's education at Kumbakonam College ended there. And Ramanujan was in fact very not satisfied with this. Again, he tried to enter Pachayappa College, which is situated in Madras. So he went to Madras and admitted there, took admission there, but once again failed his examinations at the end of that academic year because he would not study any other subject except mathematics. And luckily, we had Ramanujan's performance in that examination. So you can see that in English, maximum marks were 200 and minimum required was 70, but he scored only 38. So he failed. In Sanskrit, 100, then minimum required was 35, but he narrowly failed by getting 34. And in mathematics, he got 85 out of 150. So he passed. And in fact, in that question paper, there were many questions from geometry, but he did not try it. He was not very, he did not like geometry that much. Okay. Then, so he failed again. So since his family was poor, Ramanujan was forced to terminate his formal education. So therefore, we can say that Ramanujan was actually FA failed. Formal education was FA failed. That means in modern times, we can say that higher secondary failed. So therefore, that was his formal education. But despite that fact of failing exams, so working in isolation, Ramanujan completely devoted himself to mathematics and continued to record his discoveries in his notebooks. And initially, he worked on a slate and then recorded the final findings in the notebooks. So because the paper was not available, so he actually recorded in notebooks only the final results. So this is the one of the page, 2 pages of Ramanujan's notebook, and now these are preserved in University of Madras library. And he initially worked on a slate. And this is the slate, and luckily we have one of the slates is available, still available. And in 2016, 7th August, I and Professor Bruce Barnt, we visited, and I had the filling of the slate. So this is Ramanujan's slate, and this is the other side of the slate. Okay, so in 1909, Ramanujan married S. Janaki, but without any means of financial support, he desperately sought for a job. And Ramanujan met various people asking for help. And in particular, Ramanujan met V. Ramaswamy Iyer. He was the deputy collector of Madras Civil Service, and showed him the notebooks and asked him for a clerk's position. Iyer was also the founder of Indian Mathematical Society in 1907. Iyer thought that Ramanujan's talents would be wasted in a clerk's position. Therefore, he sent him to Nawab Bahadur R. Ramachandra Rao, a mathematician and the collector of Nellore. And R. Ramachandra Rao provided temporary financial assistance to Ramanujan after seeing his notebooks. Then Ramachandra Rao thought that if he gets some financial assistance, then Ramanujan will devote completely to mathematics. So he provided temporary financial assistance to Ramanujan. And after a few months, many people helped him to become a clerk in the Madras Port Trust office. And there he met 2 people, S. Narayan Iyer, who was also a mathematician. He was the chief accountant, so manager, and Sir Francis Spring, he was the chairman of Port Trust office. So they encouraged Ramanujan to write to British mathematicians. And Ramanujan initially wrote to 3 British mathematicians. First, he wrote to M.J.M. Hill. But Hill replied, but that was not at all encouraging, because Hill was not from the mathematics that Ramanujan was interested. He was from fluid dynamics or so. So he replied, but it was not encouraging because Ramanujan sent only the theorems, no proofs were there. And Baker and Hobson, they did not reply. And on January 16, 1913, Ramanujan wrote to famous G.H. Hardy. And Hardy got that letter. And first he thought that it might be a crank because he used to get so many crank letters from different parts of the world. But in the evening, when he set for the set with Littlewood to see what was there in the letter, then they found that some of the formulas that was sent by Ramanujan actually defeated him. So later on, Hardy wrote that they defeated me completely. I had never seen anything in the list like them before. A single look at them is enough to show that they could only be written down by a mathematician of the highest class. They must be true. If they were not true, no one would have the imagination to invent them. So I will tell you which are the formulas after seeing which Hardy commented like that. Okay. Then after many, so Hardy actually invited Ramanujan to work with him in Cambridge, but Ramanujan was, and the family was Orthodox Brahmin, and at that time they thought that if he sailed through sea, then his caste will be lost. So therefore they did not permit at first, but later on, after a lot of persuasions by other British mathematicians like Neville and Watson, so Ramanujan sailed for England on March 17, 1914. And Ramanujan wrote some very good papers, monumental papers, some of them jointly with Hardy. And many of those papers became very famous later on. And Ramanujan became Fellow of Royal Society and Fellow of Trinity College in 1918. And those were very famous fellowships. So he was the first to be honored as Fellow of Trinity College as an Indian, and he was the second Fellow of Royal Society, Indian Fellow. Unfortunately, in May 2017, and that means at the end of the third year in Cambridge, he became ill. So when he partially recovered in 1919, he returned to India in the hope of complete recovery. So they thought that Ramanujan health will be improved in India because the doctors and others thought that Ramanujan might have suffered from tuberculosis. So they hope that if he returns to India, then he may be recovered. His health may be recovered. So they sent he returned back in 1919. But unfortunately, on April 26, 1920, Ramanujan died at the age of only 32. And in fact, the probable diagnosis of Ramanujan's illness at that time was tuberculosis, then severe vitamin deficiency. Another one was liver cancer, then lead poisoning due to not cleaning cooking vessels, because Ramanujan cooked himself in England, and that was a war ration country, and he was just vegetarian. So many of his foods were actually supplied from Madras. So, hello, is it my voice is audible?
Yes, sir. Very nicely audible, sir.
Okay, so actually he was busy in doing mathematics, so he did not clean the cooking vessels properly, so there might be some lead poisoning. So those were the probable diagnosis of Ramanujan's illness. But British Dr. D.A.V. Young in 1994 made a careful examination of all records that is available and recorded symptoms of Ramanujan's illness, and convincingly concluded that Ramanujan actually suffered from hepatic amoebiasis, and that is a parasitic infection of the liver. Because Ramanujan had also some dysentery problem while he was in Madras in his when he was taking his second examination. You can see that he abstained from appearing two papers. So actually he was suffering from some dysentery type. So after all these examinations, Dr. Young, so he actually concluded that Ramanujan might have suffered from hepatic amoebiasis. The illness is difficult to diagnose, but sadly, once diagnosed, it can be readily cured. So therefore, one can actually say that Ramanujan was in fact wrongly diagnosed, and he could have been saved if properly diagnosed. Okay. The complete biography of Ramanujan was written by Robert Kanigal, the man who knew infinity. And a Hollywood movie is there, as you know, and as Dev Patel as the lead actor as Ramanujan. But I cannot imagine Dev Patel as Ramanujan, so I have not seen that movie. And okay, and there is another novel, David Leavitt, this Indian clerk, and there are many sources of Ramanujan's life, and mainly those are derived from P.V. Seswayar and Ramachandra Rao's obituary notices published after Ramanujan's death, and G.H. Hardy's recollection after his death in his collected papers. Okay. So now I come to Ramanujan's notebooks, and Ramanujan in fact left 3 notebooks, original notebooks. And the first notebook, totaling 351 pages, contains 16 chapters of loosely organized material with the remainder unorganized. And sometimes he wrote actually from backward. Right? So there are haphazard collections of 351 pages. So that was this first notebook. But he had another notebook, that is second notebook, and that is a revised enlargement of the first one. And this notebook contains 21 chapters comprising 256 pages. So those 21 chapters were organized. That means first chapter was on magic square, second chapter, etc., etc. Right? So those were organized. All 21 chapters were organized, and followed by 100 pages of miscellaneous material which were not organized. So a total of 356. And the third notebook contains only 33 pages of unorganized entries. And there are some evidences that some of these pages, some of the entries in this notebook were written in England also. Otherwise, first and second notebook, all the results were written in while Ramanujan is in India. And after Ramanujan's died in 1920, his collected papers were published in 1927. And at that time, his notebooks, Hardy thought that his notebooks should also be published along with the collected papers. But due to the financial crisis of that society, so those could not be published. So the initial editing was initiated by G.N. Watson and B.M. Wilson. But B.M. Wilson prematurely died at the age of 35. And later on, Watson also, his interest waned in editing his notebooks. But he wrote over almost 33 papers on Ramanujan's results, G.N. Watson. Okay. So, and on seeing certain formulae of Ramanujan, G.N. Watson commented that he got a thrill which is indistinguishable from the thrill which I feel when I enter the Sagrestia Nova of Capella Medici and see before me the austere beauty of the four statues representing day, night, evening, dawn. These are the famous statues erected by Michelangelo. All right. So he compared his formulas to these famous statues. And in 1950, Tata Institute of Fundamental Research, TIFR, they published a photocopy edition of the notebooks. But no editing was done. This was just a photocopy, so just pages were photocopied and binded. And the first notebook was the first volume, and second and third notebook were in the second volume. So they published in 2 volumes. And from 1977, Bruce C. Barnes of University of Illinois at Urbana-Champaign, USA, undertook the task of editing the notebooks. And he, with the help of many of his students and other co-authors, postdocs, he completed the task in 1998 by publishing the 5 volumes. Ramanujan Notebooks Part 1, 1987, then second is in 1989, third is 1991, fourth in 1994, and fifth in 1998, and all by Springer. Okay. And for the first volumes, Barnes was awarded Leroy P. Steele Prize of the American Mathematical Society because his editing was so nice. Nice means that if a result is correct and it is already proved by a mathematician before Ramanujan, then it is properly Ramanujan, then also that is referred. And if it is not proved, then that has been proved. And if a result is incorrect, then the Barnt says that why it is incorrect. So this editing is very nicely done. And Barnt compared Ramanujan to Johann Sebastian Bach, and feeling Ramanujan's devotion to mathematics, quoted from Shelley's Hymn to Intellectual Beauty. I vowed that I would dedicate my powers to thee and thine. Have I not kept the vow? Okay. So now I come to Ramanujan's mathematics. So most of us, common people, we actually know that Ramanujan's taxicab number. And people say that Ramanujan was a genius because he immediately recalled that 1729 is the sum of two cubes in two different ways. In fact, G.H. Hardy visited Ramanujan in 1919 in Putney when Ramanujan was in a hospital sanatorium. Then Hardy said that he came in a taxi whose number is 1729. 17. Then he said that this is a very dull number. But Ramanujan immediately said, no, Hardy, no, this is not a very interesting number because this can be written as a sum of two cubes in two different ways. For example, 1729 can be written as 9 cube, 10 cube, and this can also be written as 1 cube plus 12 cube. So this is the small which can be written as a sum of two cubes in two different ways. Then Hardy immediately that is there any answer for the fourth power? That means what is the smallest number which can be powers in two different ways? And Ramanujan said for a while, and he said that that might be a big number. And in fact, it was big. Later on, it can be find that this is 6050-18657. This is the number, and this is 59 to the power 4 plus 158 to the power 4. This is one way of writing this number, and the another one is 133 to the power 4 plus 134 to the power 4. And in fact, Ramanujan gave solutions of this type of problems, but this is not a new theorem because already Euler has proved almost exhausted the proof of this type. So I just skip those. But people use, so he immediately calculated that 1729 can be represented as a sum of two different ways, but that is not true. That is not correct. In fact, Ramanujan recorded his results in his notebooks. So Ramanujan was actually he in fact knew this example beforehand. Okay. So then I come to theory of partitions that has a long history, started by Bernoulli and other mathematicians in the 17th century. And partition is just a way of writing a positive integer into sum of other positive integers. For example, suppose I say take say 4 integers. I can write 4, then I can write 3 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. So there, sorry. Okay. So 1, 2, 3, 4, 5. So I can write 4 as a sum of other positive integers in 4 ways. The first way, second way, third way, fourth, fifth way. And I'm not considering 1 plus 3 as a different representation. I'm just taking that 1 plus 3 is same representation as 3 plus 1. Okay, so each of these are called partitions of 4. So these are partitions of 4. 4, 1, 2 plus 2, 2 plus 1 plus 1, 1 plus 1 plus 1 plus 1. So these are, each of them are called partitions of 4. And partition, so we denote this by P of 4 equal to 5. Okay, so P of 4 equal to 5. So in general, P of n is called a partition function. So this is the partition function, right? P of n is the partition function. And in fact, Euler, the great mathematician, 1770, sorry, I made mistake. 1706 to 1783. So, so he and this Pn grows very fast. For example, this means okay. P of 1 equal to 1 because 1 can be written on 2 and 1 plus 1. So 2 partitions of 2. Similarly, 3 I have 3 plus 1 and 1 plus 1 plus 1. So what is P3? P3 equal to 3. So if I go, then P4, we already found that P4 is 5, right? So, but it goes very rapidly because you can see that P10, how many ways then I can write? There are 32 ways. That means 10, 9 plus 1, then 8, 2, 8 plus 1 plus 1. So if you go on, then there are 42 ways. So it grows very rapidly. For example, P of 25, it will be 1958. Okay. Hello.
Sir, your screen is not visible, sir. Hello, sir. Sir, screen is not visible.
I think share screen option. Yeah, again share. Yes, it's right.
Just. Is it coming? Hello.
Yes, sir. It will be coming, sir.
Hello.
Yes, sir.
Is it coming?
Yes, yes,
Yes, sir. Yes, sir.
So you said P25 is
Yes, sir.
1958. So this is increasing. Slightly visible. This is the partition function. Similarly, P100. So it's a huge number. So you write 100, then 99 plus 1. How many ways we can write? These many ways. Huge number. So recurrence formulas from which we can calculate, and actually Major McMahon, he tabulated the values of PNs from 1 to 200. So all values he tabulated. Okay. And the second question is there any formula for this PN? Is there any formula for this PN? So there, Hardy and Ramanujan came up with a new method that is called circle method. So by using circle method and this complex analysis, they came up with a formula. This is Hardy-Ramanujan famous formula for PN, asymptotic formula. This is not the exact formula because there are some error terms here, right? Error term. So you can see that this is a very complicated formula. Though the partitions are very easy to define and very easy to calculate, at least for the small numbers, for big numbers, it is very difficult. And the asymptotic formula of Hardy and Ramanujan was very complicated. And in fact, before Hardy and Ramanujan, nobody thought how to find this formula for Pn. Okay. So, and also you notice here that there is a function hyperbolic cos. Okay. So they considered hyperbolic cos function here. And this is not the exact formula for Pn. This is not the exact formula for Pn. So, and using the same method in 1937, after Ramanujan died in 1937, so Rademacher, he found the exact formula for Pn. So this is the exact formula for Pn, and these are very complicated quantities that appear: summation, then derivatives, then lambda n, etc. But this is the exact formula. And what is the difference? Everywhere hyperbolic sign, but Hardy and Ramanujan is the exact formula by taking hyperbolic cosine. So this is one of the best contributions of Ramanujan's, and how to find the partition function. Okay. So then, not only that, Ramanujan, by looking at the McMahon's McMahon. So I told you that he tabulated that value of P1 up to P200. P200. So P200 is this.
Sir, screen is not visible.
I don't know why it is. Just a minute. Screen size. Is it coming?
Yes, sir.
I think I have some network problem. Okay. It is 999 388. These many numbers are there for P200. So Measure McMahon, he calculated this P1 up to P200 using a recurrence relation. And Ramanujan, by looking at that table, he proved this. So P of 5m plus 4, P of 5m plus 4 always congruent to 0 mod 5. And what is the meaning? This means that A is congruent to B modulo say P. This means that your A minus B will be divisible by P. Will be divisible by P. So therefore, A is congruent to 0 modulo P. This means that your A will be divisible by P. So from what we get, that of 5m plus m will be always divisible by 5. That means if m equal to 0, 1, 2, etc. So I will get what? P of 4 I will get first. For P of m 0, P of 4, then P of 9, P of 14, P of 19, etc. I will get. So Ramanujan proved that all these numbers will be divisible by 5. Okay. This may be very big, but it will be always divisible by 5. So that was the first. So there are the three famous congruences of Ramanujan. And you see that function is an additive function. That means we are getting Pn just by adding numbers. But here, this is a multiplicative function. Multiplicative. It is not a multiplicative function, but nature is multiplicative. That means it is divisibility is another contribution of Ramanujan, that before Ramanujan, nobody thought that this multiplicative nature exists. Okay. So he generalized these congruences, and they are. And in 1944, Freeman Dyson, who actually passed away just recently, who was a physicist, he defined some rank. Skip this. What is the rank? The rank is that it will divide the process, because we know that it is divisible by 5. But how will you divide a number? Right. So in which way it will divide? So this is the way that these are some mathematical formula. It says P4. P4 is 5. Okay, P4 is 5. P4, 5 groups. These 5 partitions. Similarly, P9 equal to 30. So this can be divided into 5 groups. 6. And each group corresponds to the residues of 5. That means the remainders of 5. And what are the possible limits? 0, 1, 2, 3, and 4. So one can divide these partitions into according to the remainders. All right. So that was the this rank will hold Next, for mod 11 congruence, rank will not work. So therefore, Dyson further conjectured that there is some another parameter which he called crank. Actually, jocularly he called crank, and this crank was found only in 1987 by George Andrews and Frank Garvan. Ramanujan Centenary Conference, Bart's Centenary Conference. During the conference, actually, they found what is by crank. And there are many research work is going on about rank and crank. Still, there are many results, many research in different parts of the world. Okay. So all these were initiated by Ramanujan. And there is another one, Ramanujan's most beautiful identity. What is the most beautiful identity? We already knew that these partitions of 5n plus 4 will be always divisible by 5. But Ramanujan proved more than that. He proved this one. So he proved that the generating function for plus 4 is always divisible by 5. So there is a 5 factorial. So I know that if a number x is something like 5 into y, that means what? This x is divisible by 5. So Ramanujan actually found the exact this one. So you see that this is 5 into some y. This is 5, this is a y. Right? So Ramanujan found this. And Hardy said that this is Ramanujan's most beautiful identity according to Hardy. According to Hardy, so he likes this the most. Among many hundreds of results of Ramanujan, Hardy liked this most. So therefore, nowadays we call this is Ramanujan's identity. And many researches are going on about these most beautiful identities. Okay, and just I want to quote another one. So there is another partition function Qn. This Qn, the Q is nothing but number of in the previously we considered 4, then 3 plus 1, partitions of 5, 2 plus 1 plus 1, then 1 plus 1 plus 1 plus 1. But here we consider only distinct parts, partition into distinct parts. These are all parts. So 4 and 3 plus 1, these are the partitions into distinct parts of 4. Because 2 plus 2 is not in that category, because 2 and 2 are same. Here 1 and 1 are same. Here 1 and all are same. So therefore these are partitions into distinct parts. Okay, these are partitions into distinct parts. So how many such partitions of 4 are there? There are 2 partitions. Okay, so those are 2 partitions. So the simplest of there are many congruences for this partition function, and this is the simplest one. That means what is the simplest Ramanujan type congruence for Q function? This is the simplest one. So it starts with 26, and after every 125 it will be divided. Smallest is 4, then every 5, 9, 14, etc. it will be divisible by 5. But for to this is the smallest one. Now the question is there any most beautiful version of this theorem? And the answer is yes, and this has been only in 2018, and that was by me and my student Nilufar Mana Begum. And you see that this is our formula, and this is not very easy, or it is not very nice looking, because on the left hand side I have this one. On the right hand side, 5 into y. Y is very big, but despite the fact this is the most beautiful identity, some x equal to 5y. So we have extracted this 5 beautiful type identity, and this is the only first slide, because there is another slide. So this is the full formula. This is the give an example that how the Ramanujan's this is going on. Am I audible?
Yes, sir. Yes, sir. Audible.
Because some chat messages are coming. Okay. And there are some other congruences. I just skip those. Okay. Then I come to Ramanujan's tau function. So Ramanujan is also famous for his famous tau function. So Ramanujan introduced his tau function in his paper, became one of the most famous in the history of number theory. So Ramanujan defined like the, found some congruences like this. So you see that these are the congruences modulo 5, that means divisible by 5. Ramanujan's congruences for tau function. And also in the same paper, he made 3 conjectures about tau n. And what is this first conjecture? First is that tau n is multiplicative. And tau n whenever GCD of Mn is 1. Okay. Tau of 15 equal to tau of 3 into because 3 and 5 are relatively prime. Similarly, he has some relation. Right. And number C is that he has some bound for tau of P when P is a prime. So this is the bound for tau of P. So these are the 3 famous conjectures of Ramanujan about tau n. And the first 2 conjectures were proved by Mordell in 1917. But the third one was really hard. For the first 2 also, E. Hecke, he generalizes in 1937, and he began a new, one of the most important ideas, what is called Hecke operators in modern mathematics, and which is being used in many branches. But the third one was really hard, and this was unproved for a long time, and it was proved only in behind Ramanujan's conjecture. And Deligne was awarded Fields Medal, the highest prize in mathematics, in 1978. So he worked on Ramanujan's tau function, and he generalizes this, and from that, so for that work, Deligne was awarded Fields Medal. Okay, then Ramanujan and continued fraction. So the best in this area. And what is a continued fraction? The continued fraction is just a fraction which is continued. For example, A0 by A1, these will be continued, A1, A2, 1 by A3, etc. Okay, this may not be 1, 1, 1, etc. But for a simple continued fraction, this A0 is any integer, and A1, A2, A3 are positive integers. Then we call that this is a simple continued fraction. But Ramanujan considered not simple continued fraction. He considered the other general continued fraction. He was among the best in this field. So he was a genius. So let me recall an anecdote involving Prashant Mahalanobis. So he was the founder of ISI Kolkata, famous statistician. So he was contemporary to Ramanujan. And once Mahalanobis visited Ramanujan in Cambridge to have lunch with him. The latest issue of the Strand magazine was with him. And he came across the following puzzle. This is the puzzle. This puzzle you can simply explain like this. Someone stood near a Belgian's house on a street in the town of Leuven, which had anywhere between 50 and 500 houses. So let me just briefly explain. So what is the problem is that there are 50 to 500 houses, and if you stand somewhere, the number of houses here, sum of the number of houses here, house numbers here is equal to sum of these numbers of house numbers here, and you are in somewhere in between. So what is that number? So that was the problem in that magazine. Then Mahalanobis used the method of trial and error to get the correct answer. Then Mahalanobis asked Ramanujan, here is a problem for you, Ramanujan, frying something for lunch. Please tell me. Then Mahalanobis read the problem. Then Ramanujan, he immediately told Mahalanobis, please take down the solution. And Mahalanobis was astonished that the solution was in terms of continued fraction. And Mahalanobis, he did not tell what was the continued fraction, but later on, Hartshorne and other mathematicians, they actually found that Ramanujan might have dictated the solution in terms of what? Continued fraction, this type of continued fraction. This may not be the exact one, but this is one of those continued fractions which gives the results of those type of problems. For example, if you see that this is a solution. So this is a solution. There are 8 houses. The first one, so 1 plus 2 plus 3 plus 4 plus 5. These are the house numbers. And you are in the 6th house, and 7 and 8. There are 8 this eight number houses, you see that 7 plus 8 is equal to 1 plus 2 plus 3 plus 4 plus 5. Okay, so this is 15, this is 15, and you are in the middle, 6. Similarly, if there are 49 houses, you are in the 35th. Okay, 35. Okay, so etc. So, and what is the answer of Ramanujan's result? Ramanujan's result is 204. 204. That means 1 plus 2 plus up to what? To 203 is equal to 205 plus, and what is the last one? Last one is 288. 280. So what is the answer? So answer is 204. So this is the house number of the Belgian. So Ramanujan's formula not only give the particular solution 204, but it gives all the solutions, because these are the convergence of this particular continued fraction. So Ramanujan was, you see that how he loved continued fraction. And there is a famous continued fraction named after the Rogers-Ramanujan continued fraction. And this is defined by this one. So for example, we know that this continued fraction, 1 plus 1 by 1 plus 1 by 1 plus, if I go on like this, and this is nothing but what? A root plus 1 by 2. Okay. So this is the golden ratio, 5. So I'm not, but this converges to what? Go 5. Ramanujan knew that, and in fact, every mathematics student needed, MSc student at least. So golden ratio is square root of 5 plus 1 by 2, and this is 1 by 5. This one, 1 by 5. So you see that Ramanujan's is 1 over 5. All right. So he generalized this. Instead, he found many interesting properties of this RQ, and also he evaluated this continued fraction when e to the power minus pi, etc. So these are the evaluations of Ramanujan. And actually, after seeing evaluations, Hardy and Littlewood, they were astounded. And Hardy said that they defeated me completely because they have not seen this type of evaluations before. So, and this is another one. You see that this is a connection between RQ5, that means Rogers-Ramanujan continued fraction, with argument q to the power 5 and related to q. So this is a very beautiful. On the right hand side, you see that all RQ to the 5 are there. On the left hand side, I have RQ and raised to the power 5. Okay, so these are connected, and these things are called, these relations are called modular relations or modular equations. So this is one of the best modular equations of concerning the Rogers-Ramanujan continued fraction. So Ramanujan was infamous for this continued fraction. He evaluated many values of continued fraction, found several modular equations for continued fractions. So this is what I said, that after seeing this, Hardy said that they defeated me completely, and he to work with him. And there are some other to continue fraction, so I will skip these things. So I just skip this. So these are written in his notebooks. And Ramanujan and modular equations, as I already told you, that is called a modular equation. There are many modular equations, and in his notebooks, Ramanujan recorded without proofs. Most of the formulas in Ramanujan notebooks were recorded without proofs. So that is the only problem. So people are busy in finding or deciphering what is behind those theorems. Okay, so that is a modular equation. And Ramanujan wrote many modular equations, and most of these modular equations are written in terms of alpha and xq, then is beta is equal to some x to the power, or say q of n, if n not all functions satisfy this type of modular equations. There are some special kind of functions which we call theta function. A certain kind of theta function they satisfy this type of modular equations. So Ramanujan wrote many modular equations in his notebooks without proofs. So these are Ramanujan's modular equations of degree 3. There are 5 degree 5. Then there are mixed modular equations, etc. And many might have done. I already told you that Bruce Barnes, he proved Ramanujan's most of the modular equations, and many other mathematicians also proved Ramanujan's modular equations, but they cannot say that this is the method used by Ramanujan to arrive at those modular equations. So we still do not know how Ramanujan might have arrived at those modular equations. And in fact, the modular equations of composite degree 1, 3, 7, 21, these are not at all proved. They only verified. The modern mathematicians, they only verified by using modular forms, modern techniques. And there are many partition theoretic interpretations of modular equations. And for example, Farkas and Kra, he found a partition identity involving colored partitions. Okay, so this is their identity, partition identity. I'm not going into the detail, but just you suppose that this is the partition identity. And what happens that, in fact, Ramanujan actually written this 7th order modular equations, and from this 7th order modular, Farkas and Kra partition identity immediately follows. So therefore, R. William Gosper, he once commented that Ramanujan frequently reaches his hand from his grave to snatch your theorems from you. That means, after so many efforts, one might have found one theorem of his own, but later on, that was already in Ramanujan's notebooks or Ramanujan's papers. So therefore, he said that Ramanujan frequently reaches his hand from his grave to snatch your theorems from you. And there are many such instances. In fact, Ramanujan snatches the theorems. Okay. And several more partitions identities are found by employing Ramanujan identity that we have found with Professor Barnes. So both here, you see that this is twice n and this is twice n, and this is very rare that both twice n and twice n are here. Okay, so you explain later on when I give some technical talks, then I may explain. Okay. And mock theta functions. There is another version which we call now lost notebook. Okay, so in his last letter to Hardy, dated 12th January, wrote only one paper after returning to India. And on January 2012, he wrote to Hardy that I discovered functions recently which I call mock theta functions. Okay. Then he noted down mock theta functions of orders 3, 5, and 7, and some asymptotic formula for a function of order 3. Receiving the letter, Hardy thought that Ramanujan did not say anything about his health, but Ramanujan was suffering from illness. Okay, so therefore, but Hardy thought that nothing is later, so he thought that Ramanujan might have been, that means he is improving. But actually Ramanujan died the following April. So therefore, high level mathematics, Ramanujan's wife, Janaki, he told that just before 4 days of his death, still he was doing mathematics. Proved most of the assertions since Ramanujan's letter, and 7th order mock theta function. And in 1952, Gregonet proved asymptotic formula of mock theta. 66. And in fact, George Andrews, he did his PhD in University of Pennsylvania. The other papers by Watson and Gregonet, etc. And in 1976, Andrews visited, because Watson also working on mock theta functions. So he Trinity College library, because all papers donated to Trinity College, Cambridge. And there, among Watson's papers, he found a manuscript containing 138 pages in the handwriting of Ramanujan, and that was lying in the library. And Andrews called this newly found manuscript Ramanujan's lost notebook, because it was lost for a long time. Seeing that. Okay. So that's why this law came. And according to Emma Lehmar, the discovery of Ramanujan's lost notebook was comparable to the discovery. And so you see that it has been compared to Beethoven's symphony. So in 1988, Nerosa Publishing House of New Delhi, they published Ramanujan's other unpublished manuscript of Ramanujan. In fact, it was published in the first volume was published in 1987, and it was gifted to Ramanujan's wife Janaki Gandhi. Okay. Then Andrews and Bond have edited the lost in the following 5 volumes. So this has been now completed. The first was 3rd in 2012, 4th in 2013, and 5th in 2018. But as I already said, there are many other results which are yet to be proved by using Ramanujan. There are many results yet to be proved this method. In a path-breaking paper in the Annals of Mathematics, Brinkman and Ken Ono show that Ramanujan's mock theta functions are special cases of some infinite families with half one. So this was a breakthrough that Ramanujan's mock theta functions could be interpreted in some other way. Okay. So, and Brinkman was awarded €1 million Krug Prize also. Work. And so then I came to just briefly discuss about Ramanujan's universal quadratic forms in just five minutes. So a form is called universal if it represents a brief three is the sum of 2 squares. This is 2 I can write 1 square plus 1 square, but 3 I cannot. Okay. 2 squares. This is not universal. Similar universal, because I can 3 as 1 square plus 1 square plus 1 square, 4 as 2 square plus 0 square plus 0 square, 5 also I can write, 6 also I can write, but 7 I cannot write. Theorem that this is universal. X square plus Y square plus Z square plus W square is the sum of 4 squares. And Ramanujan in 1916, what are the universal forms of this form? That means AX to D equal to 1. So he took arbitrary A, B, C, D. For what A, B, C, D is, this is a universal form. That there are 55 exact such forms. And the list was exhaustive except the form that this is not universal. This is not universal. And also, these forms are called diagonal forms. Right? So diagonal universal form, there are only 4, only 54. And in 1993, Conway and Schneeberger form having integer matrix representations, every positive integer up in, then it represents every positive integer. Okay, so I can just simply explain because I can write that x square plus y square. How can I write this as a matrix? So you see that this 1 0 0 1. So if I matrix multiply this one, so you'll see that this is just x square plus y square. So therefore, x square plus y square form is attached to integers, okay, positive integers. So, but there may not be all quadratic forms integer matrix. For example, this is not an integer matrix. What is the form? This is, I can write if I matrix multiply, then you will see that this is nothing but x square plus xy plus y square. This is also a quadratic form, but this is not integer. A quadratic form represents all integers up to 15, that all the integers. So it is enough to check on only up to 50. So that was the theorem by Conway. But this proof was not very easy. And Manjul Bhargava, the first mathematician, Indian origin mathematician, this 15 theorem in a simple way. And he found some critical numbers that any quadratic, if it represents 1, 2, 3, 5, these numbers, then it is enough to say that it will represent all other integers. Okay, and there, as a consequence, Bhargava proved that there are 204 universal quaternary forms, and out of those 204, there are 54 are there, and those are considered by Ramanujan. Problem posed by Ramanujan in 1916, or started by Ramanujan in 1916, was completely proved in 2000. Okay, and Bhargava, not for this work, but for some other work, but this is one of his famous work. He proved that is called 290 theorem, so I skip this one. Okay. So can I get another 5 minutes?
Yes, sir.
His contributions in pi. Okay, and pi we already know circumference and diameter of any circle. Okay. If we consider a smooth, circumference divided by diameter will be always same as this one. It is nowadays called this pi, and this is very late. It is only in 1906 that it came. So I'm not going to state all these things on pi, and they have long back in 6 construct a circular VD equal to a square VD, and there are in shlokas. Okay, so these are some, and Aryabhatta, he also found, he also wrote Aryabhatta. There are four portions are there, and one of the Ganit part. In Ganit part, his shloka is like that. Chaturadhikanga shatam astam gunama dwasas. Means this is the Chaturadhikam shatam. That means Chaturadhikam shatam. So 100 plus 4 into 8 astam guna plus dwasastisthasta sahasranam. So 62,000. So this is the perimeter of a circle of diameter 20,000. So this is divided by 20,000, and that is equal to 3.1416. So therefore, Aryabhatta actually found the value of pi. What is the actual value of pi now? This one, 3.14159, etc. So Aryabhatta found that 3.141 up to 1. So at least 3 decimal places he found. Okay. Famous iterative process of considering perimeter, inscribed perimeter, outer hexagon, green one and red one you see, and in between circle has diameter 1, so therefore length of the circumference the pi, value of pi, but that lies between the inscribed hexagon and outer hexagon. So that you can given that, and after 4 times doubling it, he found that and 3.142. So you see that first 3 digits are same. So therefore, okay, so this is an iterative process. So one can go on iterating and you can find more values. And this was being used before the advent of calculus. And in calculus, this great. So pi equal to an infinite series. Okay, so therefore one can find the value of pi from in this value of pi. So first method was Archimedes, and second was this, and the third. Then in the second method, actually modern computers were used and to find many digits of pi. So for example, the first electronic
So voice is breaking, sir.
Hello.
Voice is breaking, sir.
Okay. Is it coming now?
Yes, sir.
Is it all right?
Yes, sir.
Okay. So that is the and this method was used by many others, and there are many other pi algorithms found by Boron. Found over 16 million decimal places of pi. Came into picture, and many approximations of pi, and these are connected to modular equations and paper published in 1914. So he found many approximations and series related to pi. Okay, so these are the first 3 series. These were actually appeared in this High School Music. Formulas of Ramanujan, it is 4 over pi and 8 over pi. But here you see that in the second formula, I have 16 over pi. We have 16 over pi. But the teacher is writing 8 over pi. So this is a very Vanessa Hajin. So Vanessa Hajin. So, and she pointed out that that is a mistake. The teacher is correcting that. Okay. So the teacher corrects this. So this is a sequence from High School Musical, Disney film. And after offering the 3 formulas of 1 by pi, the Ramanujan said that there are some corresponding theories. Okay, but he never said how to 14 series. So there are these 4 series, and there are 5 series, and there are 5 series. So total 14 series. So there are total 17 series of examined by the alternative theories were examined by K. Kamraj University. But all of these proofs were given only in 1995. So it took so decipher Ramanujan's work on alternative theories. Okay. And in 1985, R. William Gosper, he used Ramanujan series to calculate over 17,556 and 100 digits of pi by using Ramanujan's formula. So Gosper calculated these many digits, the people thought that Ramanujan's formulas might be correct because there were no proof at that time. And that was proved by 2 brothers, Boron of Canada. They published a full book on those series, pi and the ASIN. in 1987. They succeeded in proving all 17 of Ramanujan, but they used some other techniques which are not known to Ramanujan. Okay, and they use computer extensively. So in a subsequent series of, at the same time, another two brothers, David, they also derived new series representations for 1 over pi. This is one of the most famous series of Sudnovsky's, and this is still in finding the value of pi. Okay, they calculated over 2.2 billion digits of pi. And this Mathematica, the package Mathematica, when you ask for series of Sudnovsky to calculate, that is the library function. Okay, and in the last few years, further particular series representations for 1 over pi were calculated, and many general formulas were developed, inspired by Ramanujan's work. And one main architect, Chen, he is Professor Barnes' student. And there are many other series. You can see that authors. And you see that this one is 19, this is 2020. So this paper by Wengchang Chu, it was published paper on 1 over pi, Ramanujan's formula. For Ramanujan's formula by using another new technique, hypergeometric series. Okay, and he found many other series. Ramanujan's list. So this is only in July 18th. And there are many other this one, so I will skip. So because there are some periodic analysis there. And we also contributed something. So we tried to find, we actually visited Ramanujan. Proved almost all his series and also found a plate series including series for 1 over pi square. Papers were published in 2008, 2009, 2010, and 2011. Our series, this one of 24 by pi square, that is 1 over pi square. 24 I can take to the denominator here. And this is the perfect analog of Ramanujan series for 1 over pi. And for a survey on Ramanujan type series for 1 over pi till 2008 and 9, one can see our paper published in American Mathematical Monthly, jointly written by Barnes and Chen. Okay. And there are other formulas which are inspired by Ramanujan. These are called BBP type formula. So using this BBP type formula, that means Bailey, Borwein, Plouffe, one can find the binary digits of individual binary digits of pi. Okay. So, and there are some recent pi calculations. I'll just tell you that last year, March 14, Emma Haruka, 31 trillion 215, this many digits. So you see that this is the value of pi actually, 3.159. So Haruka, she calculated even these many digits of pi. So used 25 Google Cloud virtual machines to generate the enormously long number. Okay. And the recent pi calculation record is by Timothy Mullican this year in January 29th. He calculated 50 trillion digits of pi. And most of the latest pi calculations are done by formula and Borwein's quartic algorithm. And there is a actually program devised by Alexander E. So that is called Y-Cruncher. So they use Y-Cruncher to find these many digits. But there are still unknown, this is unsolved problem. That means can we extract the individual digits of pi? That is still unsolved. Individual find exactly the 100th decimal place calculate. So those are not known. So there are many other unknown things to be known in future. And so this is one of the main contributions of Ramanujan. That after his contribution on series for 1 over pi, many new theories were developed. And at last, I want to quote from S. Raghavan, one of the finest mathematician from TIFR, that a walk through Ramanujan's garden. So this was by actually Freeman Dyson, may yet reveal many a new resplendent flower in full bloom. There is so much for every one of us to learn from Ramanujan and his monumental mathematical achievements towering before as an Everest. Hardy regretted that Ramanujan was not born 100 years earlier, during the great age of Euler, Gauss, and Jacobi. So many of the Ramanujan's formulas are in resemblance to the beautiful series of Euler, Gauss, and Jacobi. So Hardy thought that Ramanujan might have born 100 years earlier, so that he could have discussed with those people. But according to many modern mathematicians, Ramanujan should have been born 100 years later, because due to advanced computational techniques, this Mathematica, then MATLAB, Ramanujan could have excelled in other directions, every directions. So that was great Ramanujan. So at last, I have some incomplete acknowledgement. I thank Professor Bruce C. Barnes for his encouragement and wonderful collaboration, and my former and current PhD students for their collaboration, and the organizers of this webinar for inviting me to talk and interact with you. So thank you so much, and thank you all. Stay safe in this pandemic. Too much.
We were lost in your talk, sir, for the last 1 hour and 15 minutes. Thank you, sir, for your impressive session. And we have some questions from our participants. And before going to these questions, let me give an announcement here. My dear participants, you please fill up the feedback form, which is given in the chat box, and for generating your certificates. Please fill up the feedback form. And by this time, let us have the questions. I think sir is now ready. Sir, may I put a question? Yes.
Okay, let me just
okay,
switch
sir.
on the light.
Okay, sir.
Yeah,
Okay,
there
sir.
may be some disturbances from the light. Okay.
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 Sir, first question. Could you please throw some light on application of pi series? Sir, your voice is not coming, sir. You are not audible yet.
Okay. Hello.
Yeah, yes, sir. You're now audible.
Yeah, so trillions of digits were calculated. So one application is that this is the benchmark for supercomputers, one can say. So for example, David Bailey, so he used the calculation of pi to check the check supercomputers, and similarly Canada and other. So you see that to calculate so many digits, the computers require many, there may be many hardware problems, software problems, etc. Okay, so the algorithms are so extensive, so that it is expanded in various directions. So therefore, it is a very nice way of checking the supercomputers. So that is one application. And secondly, to find in trying to find to so many decimal places, there are, for example, fast Fourier transformations, then discrete Fourier transformations, and high precision multiplication. So those were all developed in trying to find the billions of millions of digits. Okay, so that is one application one can see.
Okay, sir. Second question is again in the chat box. That question is, are Ramanujan's work applicable to all kinds of series?
All kinds of series means it is not understood.
Someone is saying trigonometric series, etc.
Yeah. So he developed many trigonometric series also.
Next question is, Could you please give some idea of Ramanujan's contribution to algebraic number?
No algebraic number. No, there is no such thing. He tried various methods, but not particularly that this algebraic. I'm not getting.
Okay, sir. Sir, next question is very interesting one. One of the results in number theory is Fermat's last theorem, which was conjectured by Pierre de Fermat around 1637, and first successful proof of this was given in 1994 by Henry Wines.
Yes.
Is there any contribution of Ramanujan towards the proof of Fermat's conjecture?
No, I don't know. I don't think his methods were used there.
Okay, sir. How number theory can be applied in cryptography?
There are many ways of applying in cryptography. So it is not possible to tell in just this one. Okay, one can see Koblitz book on cryptography.
Koblitz book.
Yeah.
Yes, sir. Okay. And next question is, can Ramanujan's work be applicable be applied to this quantum mechanics, etc.?
Yeah, many physics people are applying Ramanujan's mathematics. For example, in statistical mechanics, his partition theory are applied, and in string theory, those are applied. So many such areas are there where Ramanujan's theory is applied. Okay.
Okay, thank you, sir. These are the important questions, and some questions if the participants ask during this time, then we can ask you, sir.
Okay.
So I think here we can temporarily stop. And I now would like to invite our Dean Madam, Professor Anuradha Devi, to kindly give her closing remarks. Ma'am, you are not audible. Ma'am, you are not audible.
Bhagwan.
Yes, sir.
Actually,
yes, sir.
You know, there is so much of network problem.
Yes, sir.
So much of network problem. Sometimes his voice was not coming. Sometimes the video was not seen. But otherwise,
yes,
really, it was a very, very nice lecture.
Yes, sir.
It is really thought-provoking. I really liked it. Thank you. Thank you for that.
Yes, sir.
Okay.
Yes, sir. Yes, sir. I think ma'am could not connect her voice.
Hello.
Hello, ma'am. Hello, ma'am. May I now request Professor Dr. Sir to kindly say a few words?
Hello, you are asking me?
Yes, sir. Yes, sir.
But anyway, I am very pleased and very excited by hearing the lecture delivered by Professor Teka Borua. Really, it is a very excellent talk. But nowadays, people are thinking how the outstanding contribution of Ramanujan can be used in our modern science and technology. And as far as modern science and technology is concerned, there are heavy use of suppose irrational number. How irrational number except say suppose golden ratio pi or e and other irrational number can be used in science and technology? And is there be any connection of Ramanujan contribution to the all irrational number as well? And that is the another important contribution of our chaos theory and fractal geometry. Because I want to say one thing, that one, suppose Galileo rotation. And as you know that Galileo is known as the father of modern science. And Galileo said the whole universe is written by the mathematical language, and all the figures and symbols in this great book are the mathematical geometry. And therefore, it is a message for our young, suppose students, that if you want to study the universe, or if you want to study the laws of nature, everybody should have a very working knowledge in mathematics, and everybody must have a working knowledge in mathematical geometry. And therefore, how these statements are related to the contributions of the Ramanujan, and that is also another, I think, challenging problem. Anyway, thank you very much to all.
Thank you.
Bapan, can you hear me now?
Yes, sir. Yes,
Hello.
ma'am. You are audible
Okay. I just got connected from my mobile. What can I say actually? Good afternoon, everyone. And it's really a mesmerizing talk. After such a elaborate talk, I don't have anything to say. But really, whenever I learn or I read or I listen to anybody who is talking about Ramanujan and his contribution to mathematics, it's like a going through Agatha Christie's novel. It's so much of mystery in it, and so much of mystery yet to solve, yet to resolve. So I think it's wonderful talk by Professor Noyandip Dekaborua, and we have been here. He has been collaborating with us for such a long time, and I'm so proud that you have accepted our invitation to talk in this webinar. And thank you so much. Thank you very much. And I'm sure all the universities should have some sort of a Ramanujan's discussion center, Ramanujan study center to start with. Maybe we can have weekly or monthly seminar on his contribution and what recent work has been done. As you have mentioned, 2020, there is a very nice paper written on his work. So I think however we are progressing, his mysteries, unsolved mysteries are opening up. So I think it's a very wonderful thing, and I'm sure our young mathematicians, we have learned a lot from your talk, and I'm sure we can have such kind of collaborations in our university also. And our Dr. Sir is also there, and many of the senior professors have joined us from other universities. I think we should do something about that. I mean, you are doing a wonderful job at Jaspur University, so please guide us also. So I'm sure you'll will be doing something good for maybe we are not doing enough in our country than others. I mean, in the world, I think there are a lot many work going on than our country. So I think we must do something about it. That is my just personal feeling. I hope we can do. So thank you so much, Professor Noyandip Dekaborua. I'm very much impressed. Thank you so much. Thank you very much. Okay, over to Bapan. You can conclude now, I think. If not many questions are available.
Thank you so much.
Thank you, sir.
Thank you.
Sir, VC sir, would you like to say something, some contributory remark?
I just wanted to say it was really mesmerizing session, and thank you so very much.
Yeah. Yes, sir. Yes, sir. It was really 2 hours of lecture. I mean, it was a wonderful. Thank you very much, sir.
Thank you, sir. Thank you, ma'am. Thank you, Dr. Sir, also. So now, before the end, I would like to offer our sincere thanks to Honorable Vice Chancellor, sir, Academic Chairperson, sir, Dean, madam, our speaker, sir, Professor Noyandip Dekaborua, sir, our technical team, faculty members of Department of Mathematics, other faculty members of different universities, all participants, and all well-wishers. Thank you, and thank you all. Have a good day.
Thank you very much.
Okay, thank you very much.
Thank you, Buragoy sir, for attending.
Thank you.